All right, good morning, everybody. Just kind of beginning our test review, making sure we're going to do homework today. Just any quick questions on the topics list that went up. I tried to organize this by chapter, and I might have even gotten it right. Yeah, I think I got that all right. Okay. So there are the topics. You know what to focus on, right? And again, what are we doing the Monday we get back from spring break? More review, like trying to get us back into the swing of things that day. And then Tuesday, more review, like a lot of review, right? Okay, so let's get a jump on the homework. What problems on the homework are giving you difficulties? Okay, well, okay, beyond the normal existential dread. That's a good question. 2030, right? Part 1. Well, that's not good. 48 of you have not started. Not started. Oh, look at that. Everybody else getting this one too? Just go home. We were having this problem all day yesterday with the 4A students trying to review for their stuff. And the only way I could seem to fix it was to use a different browser. Like, I think they've got cookie problems. And the only way to fix it is to nuke the browser. And most people aren't willing to like give up all their cached logins and have to put their passwords back in. So I'm just like, use a different browser. Okay, so we got there in the end. Should we step through them and see how far we get? So I know it happens a lot on the conceptual questions because I can go in and look at it. A lot of people kind of click, they try them, they kind of click, and then they get frustrated and they just click until it turns green and they move on. Perfectly viable method. But homework has never been about getting the right answer. I mean, that helps, gets you the grade, right? But homework is always about what do you understand. So the thing with Faraday's law, Lenz's law, all of the directions that you'll be asked to do on the exam, I really can't save you. Even if you like list out step by step, right? Increasing into, and then I do this, and then I do right hand rule. You either get it right or you get it wrong, right? If you get the flux change wrong in the beginning, that's kind of spells the end, right, for the whole problem. So you really, really want to practice this as much as you can, and I give you the conceptual questions so that you can really practice, right? And don't just be satisfied with the correct answer. Find out why it's correct, what's going on, right? This one looks scary because there's all these different plots, right? Okay. And then, of course, it's also scary because it's like rank them, right? Okay. Rank them in order from whatever best to least or the Olympic ranking system, right? I should have put it in student view. That's all right. All right. So, what direction are these magnetic fields, first of all? It says parallel to the z-axis. So which way is the z-axis in this picture? It's coming straight out at us, right? Straight out of the screen, out of the page. Okay. And so the magnetic field's coming out of the page at us, right? And we can see here that the magnetic fields, there's 6 different magnetic fields, right? 1, 3, 4, and 6 are changing in time, okay? But 2 and 5 are not. So if the magnetic field is static and not changing in time, what is the change in flux through this loop? It's 0, right? So what is the EMF going to be? 2 and 5 are going to be 0, right? So they're going to be in, what is it, last place? Oh, because of the negative. I didn't do the negatives. Okay. According to the EMF induced in the loop. Greatest clockwise EMF for, okay. And counterclockwise goes last. I was just doing magnitude. Okay. So, 1. Magnetic field 1. Is it increasing or decreasing? It's increasing in time, right? The positive slope on that solid line right there, okay? And so what does that mean for the flux through that loop? Remember, we've got to identify 2 things. 2 things in the very first step. We've identified that the flux is increasing. What else do we have to identify? The direction, right? Now, the direction for step number 1 of the 3-step process when you're trying to figure out Lenz's law, the increase or decrease refers to the flux, right? The direction is the direction of the magnetic field that's causing the flux. And we already established that this magnetic field is pointed which way? Out. So the 2 words we're looking for in step 1 are increasing and out. Okay? So we've established, yes? It says, right, each directed parallel to the z-axis. And if I look at this, number 1 starts positive and goes and continues to be positive. So it's positive z. 6 down here is negative z, isn't it? Okay, so I'm at positive z, and so it's directed out. So it's increasing out, right? What does Lenz's law say about that? Step 2, increase in. So what do you do with your right hand? Point what in? Thumb goes in, goes around clockwise, right? So I'll let you do the rest, but now you kind of have an orientation, right, as to what this problem is kind of asking you when it comes to Lenz's law. Do note, right, that the ones that are below the t-axis there, right, those are all negative direction, right? So just keep that in mind. All right. Three retaining loops. The loops are loops. Okay. Rank them according to the size of the induced EMF. Okay. So induced EMF, what are we talking about? Is that Lenz's law? No. It's Faraday's law of electromagnetic induction, of which Lenz's law is a part, right? Lenz's law gives us the direction that the current would be flowing in these loops, but Faraday's law would give us the size or magnitude of the EMF that is induced, right? Okay. Induced, okay. The current in the wire, and I can see that little current right there, okay? Current in that wire is constant according to this first part, okay? So what will the answer be? It requires very little thought. The current is constant. Okay, so does the current in the straight wire make a magnetic field? Yes. Does that magnetic field pass through the area of these loops? Yes. Is that magnetic field changing if the current is constant? No. What's the answer? 0. Right? Is there flux in these loops? Is there magnetic flux through those loops? Yes. We haven't even gotten to that part yet. Is the flux changing? Is it getting bigger? Is it getting smaller? No. So therefore, the EMF is 0 no matter what's going on. So in this box, what I would put greatest. Okay. But then they changed the question right here, okay? Rank the loops according if I is increasing. Okay, if the current in this wire now is increasing and getting bigger, is the flux through the loops changing? Be careful. I'll let you think about it. I don't want to steal any learning moments from you, but I'll just say be careful, right? Trying to orient you without taking away the opportunity to learn here. And maybe you guys think that's cruel. Do we cheat? No, we don't cheat. Well, there's a current in the straight wire that's causing a magnetic field around it, right? So let's look at the very first loop here, okay? What direction is the magnetic field through the top half of that loop? Out. Good. You take your thumb in the direction the current's going, right? And it's pointed out, right? What's the direction of the magnetic flux through the bottom part of the loop? In. 1 and 3 are both 0. No matter how fast the current in that wire changes, because the top and bottom are symmetric around that wire, the flux will always be 0. The change in flux will always be 0, okay? What's the only one that has any hope of having a change in flux? It's 2. So, giving too much away there. What's going on? Okay. Okay. So the onion layers, A, B, C, and D, are not real. It says they're just circular paths, right? So they're just a geometric shape for our brains to hook onto. The yellow section there in the middle, that's where the real magnetic field is, okay? And what does it say about this circular region's magnetic field? It says it's decreasing out of the page, right? Okay. So we're already getting words about Faraday's law here, right? And the decreasing out of the page is like implying that this is going to be Lenz's law. Sort of the writings on the wall there, isn't it? Okay. Now, E dot ds. So I did this on Tuesday. Remember, I wrote Faraday's law to be able to talk about, that is not right. Giving things away now. Okay. How are we going to find the circulation of electric field? We're going to look at the changing magnetic flux, right? So E dot ds, that's a circulation. Closed surface, right? For this not to be 0, it needs to go around in a circle, right? So we have to figure out, like, E dot ds for all 4 of these circles. Now, A, if we go around that circular path right there, notice how we haven't enclosed all of the magnetic field. So is the flux going to be bigger, smaller, or the same as the total magnetic field's flux? It's going to be smaller, isn't it? Okay. Same thing goes for B. It's a little bit bigger, but it's not the whole thing. But C and D both enclose what? All of the magnetic flux, right? So again, just giving you some guidance on that one. Yes. The voltage circulates, so does the electric field. That's literally the definition of voltage right there. Way back in chapter 24. All right. So same problems that we've been doing. It's just here you have to decide if your current is with the battery or against the battery, right? Okay. So I'm gonna leave you to figure that out based on what we've done already. Hopefully you'll be able to get this. Do note, right, that they're giving us directions of the magnetic fields here, right? So that one's pointed out, that one's pointed in, that one's pointed out. They can be a little bit difficult to see on the computer screens or your phone screen if you don't zoom in on it. Oh boy. Okay. In reading the problem, right? What are we being asked? What's the current? All right. And it's the current induced. Faraday's law of electromagnetic induction. No surprise, that's the chapter we're in, right? How are we going to, where do you want to start? You want to start with how do we find the current from this thing? Or, so the easier version of this is just to say, well, this is the EMF. And then Mr. Balogh just ignores Lenz's law when he's going for magnitudes, okay? So if we are careful about the change in magnetic flux, now we've got solenoids within solenoids here, right? We got a solenoid on the inside and a coil on the outside, which technically is a solenoid anyway, right? So the solenoid is making a magnetic field. And from last chapter, we have an equation for the magnetic field of a solenoid. That solenoid's magnetic field changes, so there's a changing flux through the coil on the outside. By the way, this is how your toothbrush works. If you have a mechanical or electric toothbrush, you put it on its charging stand. It's usually got a pokey, right, and a divot in the bottom of your, right, okay? It's just two coils, a solenoid in one and a coil in the other, and this is how they charge. So you're going to find the change in flux of the coil because you know the magnetic field of a solenoid. What's the thing that's changing here? Is it B, is it A, or is it cosine theta? Because those are the only three things that can be in flux. It's the strength of the magnetic field, right? You have a delta T, so you think of these D's as deltas now, right? So it'll be a changing current in that magnetic field of the solenoid. All right, they don't ask me for direction, they just want the magnitude, right? So we get the EMF. Let's say we can do all that, we can get this voltage. How do you find the current? Meditate on it. Ohm's law, right? V equals IR, but what's V? You just found it. V and EMF, same idea. Right? And they gave me the resistance, right? Yeah. So 0.9 ohms. So can find current. If you know the voltage, you know the current. As long as you know the resistance. Okay. I already know the answer and I haven't read the problem. It better be 0, unless there's something I don't understand. It's centered. The current changes. Why is it 0? It's symmetric. Is there flux through this coil? No. There's magnetic field that comes out at the top and in at the bottom. Every field line that's coming around this thing comes out through the top and passes right back in. What's the flux? I don't care how much the current in that wire changes, there's still 0 flux in that round coil. So in this case, there's no flux, and no matter how much the field changes, the NE is equal to the outie or whatever, right? And so the answer is 0. Am I going to put that one on the test? Now that I've just done it for you, because you guys know I just put everything I say on the exams, right? It's how my exams work. No, that's not what I do. Now, could there be something like this on the exam? Conceptual, maybe, right? Because I do think this was a conceptual question. I don't think this is a calculation question, right? And even, like, I'm suspicious every time I see something that's symmetrical, right? When I see a loop centered on a wire, I'm like, there's nothing going on here unless they're asking for something else, right? So, watch out. Uh-oh. This one doesn't look very symmetrical. Yeah, it depends what axis you want to draw to. Yeah, the problem is this field only goes one direction through the loop, right? There's no other side of the magnetic field that's going in, right? So I've got only field coming out of the screen at me. Milliwebers. Oh, that's a cute unit. The Weber is the unit of magnetic flux. If I'm asking for flux, the units will be Webers. Actually, technically, they would be Webers, but we don't say that on this side of the Atlantic Ocean. He was German, so his last name would have been pronounced Weber. They don't have W's. Their W's are pronounced V's. Weber. So milliwebers. Why do Germans always sound angry? Anyway, shouldn't say things like that on YouTube. What is the magnitude of the... I've met lots of Germans. They're really nice. They're nice. They just sound angry. What is the magnitude of the EMF? Okay. All right. Okay. So they gave me the flux function, the flux as a function of time. What does that suggest about, like, kind of what form you're going to use over here? It's definitely Faraday's law, but, like, is it a delta or is it little d's? It's little d's, right? And not being given a time interval, we can assume the time interval is instantaneous. And so we're doing a derivative, which is a ratio. It's a way of doing ratios, right? So can we take the derivative of t squared in t? Is that something we can remember how to do? Okay, right? Now, the first question, though, doesn't require a derivative, does it? No, it does. It does. Because they're asking me for EMF, right? At a certain time. So you're going to find the EMF, and then when you find the EMF, there's going to be a t floating around in there, right? Because t squared is 2t, right? And so then you just put in the time. This is like functional mathematics. And then, direction. Okay. As soon as they start asking about direction with Faraday's law of electromagnetic induction, what are you doing? You're using Lenz's law. So have fun. Okay. This is asymmetric. Why is this asymmetric or not symmetric? I mean, it looks symmetrical. It's got triangle on top, triangle on bottom, right? But what's the asymmetry here? There's magnetic field in only half of it, right? So there's an asymmetry here. I gotta be a little bit careful. It's a square, but it looks like a diamond. Okay, half the battery magnitude. Oh, another time thing. Okay, and then they want the EMF and the direction. So this is like the last problem. Okay, but as far as your area is concerned, is it the area of the entire square? No, it's only the area where the magnetic field is passing through, right? Is this kind of thing helpful to you or not? Mr. Balogh, why haven't you done this on every homework assignment? It's a fair question that I'm not sure I have an answer to other than I never have time. Oh, garbage. Yeah. I remember assigning this one. When is this homework due? But that's the Monday we come back, right? Okay, so you guys can kill me that day. Okay. Does anybody see the problem with this problem?
There is a velocity of the square. That's not a square. The rectangle. I was close. Oh, the loop is moving.
What does that mean?
Flux is changing. Oh no, the areas. No. Distance is changing. Theta is changing. God, what?
Still don't see it, do you? The magnetic field of a wire depends on what?
E equals mu naught
I don't remember. Is it 2 pi r? It depends on how far away you are from the wire. If this whole rectangle is moving away from this wire, you're going to end up with some sort of dr dt. To figure out the flux, it's the distance from the wire that is changing, right? Is the area of the loop changing? Is the angle changing? It's the magnetic field strength that's changing. And the challenge in this problem is coming up with an expression for how that flux is changing in terms of V. Yeah. You could just wait for Monday for this one. Okay. But this is a challenge, right? This is a challenge for finding the change in flux. It's a good problem, but it's a challenge. No. It is question 9 of 10, not 11 of 10. What's that? Let's find out. Not that bad. They told us, they gave us milliteslas per second. What have they given us? That's delta B over delta T. It's not quite the flux, right? Because the flux has to have an area attached to it. But they just gave us dB/dt. Yeah, if you got instantaneous time, versus longer, not instantaneous periods of time. That statement suggests that a fundamental understanding of what this symbol means needs help. What does this symbol mean? A little change, right? What does this symbol mean? A bigger change, okay? How do you get from this symbol to this symbol? What are they teaching you in math? I'm going to have words with Mr. Woods. In the limit, as delta t goes to what?
Bro, limits, that was about a year ago, sir.
Still. How small is delta t getting? In other words? Okay. Is this fundamental theorem of calculus, anybody? More than a year ago, and it had nothing to do with your life, and now all of a sudden it's come back at you like a lion jumping out of the weeds? No. So, do we have to do this? Do we have to take the limit of this thing? No, because this just turns into this. Yeah. It's the power of calculus, right? So when you have a delta t of 1 second, you just know your delta t, you're done, right? Or 3 milliseconds or nanoseconds. I don't care if you've got a duration of time that you know more. However, if you know a function and how it's changing with time, and you need to find out your values everywhere along that function, what do? Take a derivative, which is nothing more than this same ratio squeezed down to infinitesimally small pieces of time. Here, they gave me the dB dt. D magnetic field per dt is 7.01 in my, times 10 to the minus 3 in my problem right here, right? So setting up the flux, right? Okay, they're going to give me the dB dt in here. Because this flux, how do you write this flux again? I'm getting kind of low on the board here. D, and then it's BA cosine theta, and you just hope that only one of those depends on t. If more than one of them depends on t, you're in senior level E and M. You stop doing integral derivative calculus and you do something else. Vector calculus. Anyway. So, find the thing that changes. So if A doesn't change, what do? Where do you put it? Right? Cosine theta doesn't change, where do you put it? And then you're left with dB dt. 7.01 times 10 to the minus 3 Teslas per second.
Can we cover like general types of problems and what type of right-hand rule we use for each of them?
Sure. You gonna give me a problem? Do you not remember my beautiful table? I had a table for this. Oh, yeah, I had pictures on it. I think I had it in chapter 29. Yeah, it's right here.
That's for all of them?
It's for all of them.
Is EMF a force?
No. It's got a bad name because EMF stands for electromotive force. But it's because they were idiots. No, they weren't idiots. They just had no idea what they were doing. It's unfair to call them idiots because they didn't have all the information. So they called it the electromotive force because they thought about it in terms of like, they thought electricity was like fluid. And so they thought of it like pressure. There was like pressure in a wire. But anyway, that all turned out to be wrong. But the name stuck. Just like, I hate this term, orbital in quantum mechanics. That is the worst. Orbital and spin. If there were two things in physics I would change the name of, it would be those. Because it is not, none of those words do not match what's going on. No! See? This is the contention I've made since I started my career. Anyway, historical inertia aside, the answer to your question, Lewis, is this page. Now, for those of you that are looking at this going, well, Faraday's law, Lenz's law isn't on this screen. Yes, it is. What are the right-hand rules that we are using in Lenz's law? They're both hitchhiker rules, right? And we are finding magnetic fields of loops, right? The current direct, and so it's a reversal of this one. Instead of finding the field of a loop, we know the direction the loop is creating magnetic field to fight the change, and we then use it to get our finger. So it's here. All of them are here in this table. Not copyright by me. You are free to distribute this. Put it on, I don't care. I've already posted on, I don't care. I don't, fine, go make profit. I don't care. People are like, you're stupid, you should monetize what you do. I got enough money. Don't need more. What's that? I'm not, I mean, people are you rich? And I'm like, yeah. Yeah, no. I have a wife and kids, and I can afford to feed them and clothe them. I'm rich. I've got a house. I got a couple of cars. Okay? Now, do we have to like pinch our pennies and budget and all that sort of stuff? Absolutely, right? I don't go on vacation, some exotic location every year. I do like once every 5 or 10, right? Because we save up for it. So people are like, how do you have a car? I saved up for it. What did you do before then? I rode a bike. Like, so now, my family, we survive on one income. My wife doesn't work. Well, that's not true. She works really hard. She doesn't get paid for her work. Her work is keep the rest of us alive and sane. So she made that choice, and I am grateful for it. But yes, no, in my experience, rich isn't what you think it is. It's not, definitely not a number. Now, a lot of my friends are like, you're an idiot, you're stupid, you should be out leveraging your money and make it work for you. And I'm like, yeah, I'll be okay. But I should go build what? Oh, that's not what I heard. What I heard was you should go build rocks. My grandfather was a stonemason, so it's in my blood somewhere. Right? It's these kinds of things that I'm just like, we're doomed. Selling a pet rock for 1.3 million. A non-fungible token selling for, I'm like, it's not that I don't know how to make money, it's just I don't really want to. Because I know the kind of person I'd turn into. And I don't want to go there. How do we get on this topic? Good grief. Sorry, I am not your father. You go do what you want. Okay? But But my advice would be don't take advantage of your fellow man or woman, right? Work together to make it happen. So we have too many problems where we start taking advantage of each other. All right. Other questions? We went through the homework. What else do you need to be able to like kind of get as much done as you need to before spring break starts? Yes.
Can you go over number 10 on homework
29, number 10? I don't know. Can I? You guys tend to be smarter than me, so. Oh, wait. You know what? I bet you I've got to do this and do that and then do this. Oops. No. Go. No. They all start with A's. There we go. 29. Oh, most of you did that homework. That's good. And by did, I mean there's a thing that says that it happened. You may not have understood it. I've noticed that since ChatGPT, homework scores have been very high. What number was it? 10. That was not number 10. Yeah, it was number 10. This one right here? Okay, yeah. This one, okay, I get it. I understand what's going on. Because everybody struggles with this one. Let's get this copied. Put over here so I can write stuff down. Where is my, right there. I'm going to put this one right in the middle so I can write on it. Okay. What are they asking me to find? Net magnetic field, right? That's what they want. And they want it right here. Okay. So there's two wires. I'm going to find the total magnetic field by finding the magnetic field of one wire, finding the magnetic field of the second wire separately, and then doing what? Adding them together, right? Their magnetic field is a vector. I can add vectors together. Okay. So that means that I have to find, let's start with the top one. Okay. So the magnetic field of that wire. So conceptually, like visually, the wire's got current coming out of the screen. So I take my thumb, I point it out of the screen. It's a straight wire coming out of the screen, and my hand wraps around the wire which way? Clockwise or counterclockwise? Counterclockwise. So what I'm imagining in my brain is like magnetic fields that are kind of going around like this, right? Spreading out everywhere in the page, right? But what I need is the magnetic field going through P, right? So I'm going to draw just a dotted line here so that I can sort of keep track, right, of where I am. So that's like a distance r, right? And the magnetic field of a wire, we just wrote, I just erased it because I am that brilliant. Mu naught I, was it 2 pi r? All right, so there's my r. I know my, I know my distance? They give me d2 and I do know my distances, right? Because this is d1 over 2. That's a d2. How do I find my distance r? Right? Good old Pythagoras coming out again. All right, so I found the distance. I can plug it. That'll get me my magnitude, right? That'll get me my number, my strength of my magnetic field. But what direction is the magnetic field at that point? Again, I need to imagine, right, that this is like a big circle coming around, right? And the direction that the magnetic field is going is a counterclockwise direction. So at a singular point, what direction do we draw the magnetic field in order for it to circulate? We draw it tangentially. It makes a right angle with that distance. No, the current is a straight wire coming out of the page. Magnetic fields are circles around wires. It's just at every point there is a tangential component of the magnetic field. That's how you get that field line that goes around in a circle, right? And so I'm looking at this. I'm going, okay, here's the radius of my circle, and at this point, it's got to be going in the counterclockwise direction to carry me around like this, right? So I draw. There's my magnetic field for that. Okay. So I've got to go find that direction. I know B, like B is just sitting up here, right? But I've got to be able to find this angle here, right? So how do I find any of these angles? Well, can I find that angle in there? Yeah, I've got the legs of the triangle, don't I? So I can find that angle. This is a right triangle right here. And so, and then because I know that this is a 90-degree angle, I can like find this total angle. And then I can like subtract 90 from it if I want that angle right there. I just, what angle do you want? Figure out a coordinate system and go with it, okay? So we'd have to do all that just for that top wire. What do we do for the bottom wire? Same thing. Luckily, the radius is already figured out for me, right? That is not a new Pythagoras. That is the same Pythagoras, same toga, same white hairdo, everything. Okay, what direction is this one pointed? At point P. Perpendicular to the radius. It's the same distance, it's the same current. So these two B's are the same, right? Can you tell me something about their x components? They're going to cancel each other, right? Because same magnitude, and it looks like we've got some symmetries going on here with some of these components. So it looks like I just need to find the y component of these two, double that answer, and then I'll have my answer for which direction it points. So I think this problem is, the difficulty of this problem is geometry and trig and figuring out those angles, right? Once you figured out the angle for one of them, you know the angle for the other. And only look for the y components, and away you go. So I'll leave the explanation at that with the note that at this point you can now go to the solution button and see what they do. They tend to skip steps in the solutions, so but they're pulling off the y component right there. So, did I answer your question? Very good.